So welcome to the One Word Probability Seminar. Today we are very happy to have our first speaker, Maria Eulàlia Vares, who is one of the most important Latin American probabilists. She is well known for her work in large deviation theory and well in many things, including the contact process. She had many important positions, including chief editor of Annals of Probability. And today she will present the talk Renewal Contact Process and Contact Process on Dynamic Random Environments. Thank you very much for being here, Maria Eulàlia.
Thank you very much for this very kind opportunity that is. So I'm going to be talking about mostly the first part, which is related to renewal contact process, and dynamic environments will be mostly, we will stay, Daniel will be more specialized on that case. I'm going to do kind of an introduction in some sense, and this is based on the joint work with Luis Renato Fontes from São Paulo, Marcelo Hilário from Minas Gerais, Domingos Marchetti, also from São Paulo, Tom Mumford from Lausanne, Daniel Ungaretti, who is my colleague here at Rio de Janeiro, and Daniel Valesin is with us. So since there might be students, let me start by a very gentle introduction, recalling the basic process, which is the Harris contact process, introduced almost 50 years ago, and which is a very simple and popular model for very elementary in some sense and very robust from the other side for simplified model for an infection, which is a Markovian dynamics. So imagine that you have a graph, sort of regular graph, connected, bounded degree. We are going to take ZD here. And you imagine that on each side of your vertex of your graph, you have an individual, and this individual could be infected or healthy. And I'm going to use 1 to means that the individual is infected, my configuration, and 0 means that it's health at the time. So you have an evolution, a time evolution on this configuration space. So the evolution goes as follows. The infected individual may transmit the infection with a given rate lambda, which is unique parameter of your model, to any healthy neighbor. And it may be cured with rate 1, everything independent. So the important thing of this model is that it presents a phase transition. So in quite general setup, it has this dynamic of phase transition. So if lambda is small, and you start with a finite configuration, say here I'm putting 0, just to indicate I start with 1 infected individual at the origin, then the infection will die out. So at some point you will reach the empty configuration and remain there, so subcritical. And if lambda is large, then the infection stays forever with positive probability, and you have a non-trivial ergodic situation. So you can look at this process as a sort of percolation model, and this is indeed an important way that motivated us, and in some way also was very well explored by Harris, and that's called the Harris graphical construction. So you think that you have this sort of a random graph, which you have on each side, you have on each timeline of a vertex, you have a marks, these blue marks. They are simply Poisson point process with rate 1. And for each oriented edge of between the neighbors, you have a Poisson point process of rate lambda, which are these arrows, horizontal arrows. And you think of the percolation process, which is oriented in time, and which you construct paths which can move on the vertical lines, provided they don't cross any blue mark. And they can move to the side, to the neighbor, only when there is an error. So you have this simple thing of path. And the survival of the infection means that you have percolation. So that was this which motivated us to consider looking at the process in this way. It's natural to imagine that these point processes could be more general, not only the Poisson process. And that's what that's how we started this discussion some years ago. In fact, our motivation came from a question in long-range percolation. So you have the same construction, the process constructed by the path. So at time t, you are going to have all those that you can be reached by a path. This path is not allowed to cross any blue mark. And you want to investigate the same questions which were mentioned before. Do you have a phase transition or not? So the simplest thing we can imagine for a point process here could be replace the Poisson process by independent renewal process. We had independent Poisson process. Now we are going to take a more general renewal process. And basically, we are going to be looking at two cases. what I'm going to call site renewal, when these transmissions are kept as Poisson with rate lambda, and the cure marks are a more general renewal process with a given inter-arrival distribution. So our parameters are lambda and this measure mu, which is the inter-arrival distribution, which we are going to assume, of course, not non-degenerated, and a few other conditions that will appear as we go. Of course, you could also think that you do this modification on the edge, and you call the edge renewals. That means you keep the cure marks as Poisson, and you modify the renewal marks. I'm going to focus mostly on the first, the site renewals, not only because it was the one we started studying first, but because if you think from an epidemic model, it's very artificial to have the cure marks after exponential times. So that's sort of more natural. But mathematically, we could make more general good thing. Well, there is the first thing that you immediately note that you no longer have the Markov property. There is another important property of the contact process, because it's done on the Poisson process. So you can think of continuous limit of Bernoulli of percolation, which is the FKG property. Here it might be kept or not, it depends on mu. If mu has a decreasing hazard rate, then you still keep this property and might be useful. But in general, it's also lost. So, and the first questions which I want to know, we addressed is, if mu has a heavy tail, do we have survival for any lambda positive? That's what we call the persistent survival. That means that if I start with one individual, there is a positive probability that the infection remains forever, no matter how small is lambda. The mu is fixed, and I change only lambda. So I'm on this slide, I'm putting two questions which have to do with mu having heavy tail. So if I were looking on the edges, then the analogous question would be, if mu, that means the transmissions are very rare, because you have mu has a very heavy tail, you expect that for any small delta, maybe the process does not survive. That means I'm calling it immunity, though maybe this name is not the best one. I'm going to focus mostly on this, but these questions are somehow very related. So, and one reason to tell today about the case when only one parameter, only one of the point process has been modified to a general situation, which is a good thing, is that you still keep monotonicity in the parameters. As lambda grow, you have more infection. As delta grow, you have less infection. So that's one thing that simplifies. But the first question that I want to address is this one. If conditions to guarantee persistent survival of the process. And since we are in this situation, which if I fix a time t, how long I still have until the next cure mark will depend on my measure in a more subtle way. It's natural to think, well, if you are you need to evoke the renewal processes, say if I look at time t, I should be able to say something about the remaining time until the next mark, or the time since the last one. That's so-called the age process and the overshooting process in renewal theory. So if you assume that your measure mu is in the domain of attraction of some stable distribution with alpha less than 1, because we want heavy tails, then you should be able to dispose of, you are able to dispose of the strong renewal theorem, and you can explore that. But maybe this is too much for what we want. Maybe we don't need such a precise regularity on the measure. And that's what we first try to do, focusing on the first question that I mentioned. And this was the first result that that led us to start working more on this problem. And that was some years ago, assuming that I have a dimension 1 or bigger, because if I have some regularity conditions, which are much weaker than domain of attraction of a stable, just saying that this allows to oscillate, the tail can oscillate between one power and another. You have a big flexibility, but it gives you some regularity on the distribution. And you have a heavy tail, which is condition C prime. Then indeed you do have persistent survival. That means no matter how small is lambda, with positive probability, starting from one infected individual, then the infection stays forever with positive probability. Well, this immediately brings you to think the following. Well, it's okay, you have survival, but does the infection come back? Do you have some convergence? No? Because, say, if you look at the contact process in a graph like a tree, a non-annealed graph, you might have survival, but the infection moves away and maybe it doesn't come back. You have two different phase transitions, at least. So it's natural, the first question to ask is if this happens here or not. So for that, in order to prove that you do have a convergence theorem, that means not only the infection comes back, but you can write a convergence theorem for the distribution, as in the contact process. We needed to strengthen this condition C prime a little bit. And the way we do is by saying that the tail, you have an upper bound on the tail also, not too slow. But that was, I think we may think of that as a technical condition, that we don't know how to move without it, but for this year, but it might be only technical. And we can prove is that under these conditions, so the same regularities, which are not much, but strengthen the C prime now in this way, given that it survives, you do have a full measure. That means your process, for any lambda positive, your process does converge to this mixed, convex combinations of the measure which everyone is infected and the one with nobody is infected, of course. So this says that not only the infection comes back, but if you look large times, then given that it survived, then with a large probability you find the individual infected.
Sorry, can't you repeat what is the difference in the condition C? What changed?
That was this one. The upper bound was not present in the previous. That's the difference.
Thank you.
And it might be purely technical, but we don't know how to do without it.
May I ask also quickly interrupt?
Sure, sure.
I don't understand. This looks like the upper invariant law is everybody infected.
Yes, but it's a weak convergence. So I look at a finite box, and then given that it survives forever, then with probability going to 1, I see everyone infected.
But there are still these recoveries. They are heavy-tailed, but here and there you will see
There is,
recoveries.
but
Don't they
that's
create empty sites?
they create empty sites. This is just improbability. Given that it survives, then the probability, if I look at a given time, the probability that I see the origin effect goes to 1.
Well, my intuition is
Given
not working here.
it's
But thanks.
condition on survival. Condition on survival, I'll see a lot of guys. It's in probability. It's convergence in law only.
Oh, okay, thanks.
So I give a very quick explanation on how theorem 1 goes. Theorem 1 is just saying that I have survival. So as you can imagine, since the tail is heavy, then you expect that you start creating long intervals without cures, and they are not too far from each other, and you can tunnel. The infection can go from one to the other and can go on, and you have some situation like this one. Okay, so that means you are going to have, say, it's a kind of Pirate argument, let us say. No, you have a long interval without cures, and not far from this, you have another one, which is, say, long 4 times, maybe 2 times, and then you have another one, and in between them, you have a little piece, which is little but not so little. I mean, it grows as t goes to infinite, free of infections, and your Poisson process simply goes through. So let me say what is the condition that guarantees that, and that's something which we had to prove. So if you look at intervals which are big, there exists some T1, such that if you consider time intervals of length larger than this T1, inside this time interval, you find another one, a bit smaller, much smaller maybe, but T to the gamma. This gamma is something which will depend on your distribution, depends on that epsilon which was in the condition, such that this will be empty, no cure marks with very large probability. The probability to have a cure mark in this interval J will decay as T to the minus gamma. So this, if I think of this picture, this interval would be somewhere inside of my corridor here, but I have a corridor. Just that I don't know very well where it is, because my interval I is much bigger than J. I has length T, and J has length T to the gamma. It is somewhere inside I, but I cannot localize it perfectly. So, but this is something which to get that, you don't need the upper condition in C, only C prime. On the other hand, if you put the strength condition, then you can prove that you can localize this corridor in the sense that you can find a given positive gamma such that for all intervals which are far away from the origin, T is large, the probability that the interval of the length T to the gamma has a cure mark decays. So you fix this interval, you know that with very large probability you have no cure mark. So this condition, we use this condition in the proof of the complete convergence, and in order to have it, we used the upper tail in the condition. That's the situation which we have. So let me say a few words about the proof of this one. So it's simple to imagine this drawing which I had before. I have these levels, which are here L0 is 0, L1, and so on, which are, say, there is some T0 which to be fixed, which to start with. Somehow you might think it large. No, it is large. And then you look at the next time, next site. In fact, I'm saying time, but it's in fact the next vertex, say to the right, we take dimension 1, that you find an interval which has starting at this T0, and it's 4 times. This is a certain S, this is 4 times S. So the ratio is fixed. So the first time that you find this. So just using the regularity, the probability to have this is to have this interval empty is positive if T is large. And that allows you to immediately see that in control like biogeometric. So the probability that Li is smaller than the previous plus a constant times I, this one is goes to 1 very fast, exponentially fast. It's like you bound biogeometric. So, and here only the regularity plays a role. So this is just saying that I find these barriers. My drawing is not good in the sense that this was done for another situation. So the dimensions are not really corresponding, but it is the picture what I have. So you have this, each time is these intervals without cures, they are growing like that. So T0 to the I to 4 times T0 to the I. And this for, so the next condition, which is the one that you, since this, the difference between them is not too large, no? And then you have this interval free of cures, you can find with good probability a tunnel between Li minus 1 and Li, a tunnel inside your interval, this one. But the tunnel is smaller than the size. And this is a second thing which allows me to tunnel the infection, because I will have this without cures. So just it will depend that there is a transmission path of the Poisson, so just a Poisson process between Li minus 1 to Li. So if you have these conditions, then you proceed, the infection goes to the next vertex, the next Li. And so it's like in the Peyer's argument. So if this event, the good events happen with very large probability, so the complement of this event, GI is the 3 conditions which I had, this is the case exponentially fast, then you have a positive probability of keeping forever, provided you start with infected first step, no? And there is no cures there. So this is the way you prove the first theorem, which is somehow very simple, extremely simple, and not difficult at all. But
I also ask one question.
Sure.
Thank you. About the number of levels, how do you determine it? Is it fixed or random, even a graph?
No, I'm talking, this is
Yes.
on the Z.
Sure.
I'm looking, but since I want to show that it survives, so it's enough I consider D equal 1. I don't know if I understood your question.
I was talking
The graph
about
that I'm
eyes.
looking,
Yeah.
the graph that I'm looking, it's one Z, but maybe you asked something else.
Oh, maybe then.
Okay. Well, for theorem 2, what happens is that it will, the idea is simple. No, you have this tunneling event, and now you want it to tunnel back to the origin because you fix a time t and conditioning on surviving, on that the process survives. You'd like to show that with large probability you have it infected. So you want to have a tunnel back, but you want to fix a time that you are going to look at the distribution. So you need this interval, this free of cure marks, to be localized, to be that you know where it is. And for that, we needed that condition G, which required the strong, which might look artificial, condition on the measure mu, because it's not very natural that you need to ask some condition on the tail from that side. But the point is that you need to control if dependence also, no? Because your tunnel back, you need to control the influence from what is below. So it's somehow not so difficult to imagine that some measure, some condition like that is helpful to get any proof, because whenever you want to have independence of something, you need to put a renewal, because that's the only way you guarantee that what comes next is independent. And that's why it is. But with that condition, what we can prove is that maybe it's somehow related to the question which you asked in the beginning, is that if you condition on survival, then with high probability for all t large, you find someone that is localized in this way, and this guy will stay infected for a long interval. So this is very small compared to t, and in all this strip of time, this guy will remain infected. It's like a hub that keeps transmitting the infection because it stays for a long time. It's those super spreaders in some sense, but it's not a super spreader, just that it stays infected for a very long time. So no matter how small is the rate, it has a possibility of transmitting to its neighbors. That's why it goes. There is something else you could say about this process. If instead of just these conditions that I put, you assume that your measure mu is in the domain of attraction of a stable law. And one thing very important, very interesting, is that Fontes, Gomez, and Sanchez in 20 proved that you can have survival even in finite graphs. But this their proof demands something more. The other thing which you might investigate is, well, suppose now you not only condition on survival, but you fix all the renewals. So the condition on survival and the renewal marks, they are all given. What can you say about the probability of having an infected guy at time t condition on all this? That's much more involved to prove, but using the same ABC conditions, you can prove something. And there is an interesting change of behavior as alpha approaches 1. You can say what is the probability condition on the survival and the renewals, because it has to do with the age process in a more delicate way. I don't want to enter into this because it already gets a bit too far from my goal today, which is to discuss both survival and extinction, since I want to discuss something on extinction, and this is more technical. I don't want to spend the time on that. The second question is, well, now let's go to the other side. We put some moment condition on mu, some tail condition. Now that in the case, it doesn't have heavy tail. And what do we need to guarantee that lambda critical is positive? The easy thing, which is trivial, is that if it has a second moment, simply because if the measure has a second moment, then the time interval that contains a point free of cures has a first moment. So you can compare this process with a sort of a branching process, and you see that there is no way to, if lambda is small, it doesn't survive. But this is too simple, and it's too far from what you expect. So the question which is still open is, can we simply prove, is it true that a finite first moment already guarantees this? We don't know. What we know is a little bit more than first moment. And this, in the general situation, what we can prove, general I'm saying for ZD, any dimension, because about this thing of extinction, it's very different. I mean, one dimension is very, very peculiar because there is the crossing property of the path that you can use, and this is lost in higher dimension. That's just a question of planarity of the graph or not. But so what we have for the moment is this. Any dimension, you need a little bit more than first moment. You need x times this function here with a condition on this theta, which of course has to do with our proof, has no specific meaning, but that's the way we prove. If we have something like that, then we can prove that lambda critical is positive. And let me say a little bit about the proof. I don't know how many minutes do I have, but I would like to say a little bit. I hope I can. So the idea is to use multi-scale renormalization, and I hope to explain. And the basic tool, like before we had this gap tool, now the tool is to say, well, if you have a measure, this is just a general question about renewal. If you have a measure that the mu which integrates x times f, then the probability that you have a gap here in an interval of length u decays to 0 as u goes to infinity in this way. It's this is a basic application. It's an application of the renewal theorem. Of course, whenever you have integrable, you could find some f that goes to infinity now, so that this goes to 0. But the point is that in order to create to use the multi-scale renormalization to be able to prove that it doesn't percolate things, you need some conditions on f, and that's where it comes that the condition in the theorem. So the basic renormalization has to do with, as usual, the following. You choose, say, let us say that this, you think here that d is 2 because it's enough, and you have a time parameter which has to be chosen, and here I have squares of length 2 to the n on the space, and you need to control the crossings because your goal is to say that you do not have an infinite path. So there are 4 types of crossings. You can cross in the space in any direction, you can cross in time, But for the proof, it will also play a role for the way we argue to have half crossings. Just you can think that's just a technical thing, but it plays a crucial role. So a half means I have half of the space crossing in the space or half in time. And something which is immediate from the fact that you do have the paths are nearest neighbors and so on, that the probability that there is an infinite path is bounded by these two things, or it goes up to half of the box in the time direction, or it goes in one of the sides of the box. It has to go up. So you have this estimate. So you would like to prove that these guys go to zero if lambda is small. That's the goal. In order to do that, you need to develop some recursive inequality. And in order to do this recursive inequality, one important trick is that you take the supremum, because whenever you look above, you don't know exactly where the last renewals are. So you take these numbers, which I call Sn, which is the supremum of these probabilities of having a space crossing. And this supremum means that I take all renewal measures starting below the floor of the box. No, it could start in different places. And the same for the half crossing, the same for the time crossing, and the same for the time half crossing. Okay, there are some relations which are obvious, no? Probability of time crossing is less or equal than the half crossing. Here it's just inclusion. And as in the space you have independent processes, then it's also easy to see that the Sn is less or equal than squared of Hn, because take the supremum, just by spatial independence of the renewals. And if I want to prove, our goal is to prove that if lambda is small enough, this probability goes to zero. So we need to develop some recursion. And the basic recursion could be thought as this. Suppose our boxes, Bn is large, that the half crossing contains 3 pieces of the previous scale. So you have this half of Bn contains this. So that's this condition here. And now you imagine that if you have a Q mark that's say a dual, it could be a closed dual path, no? So this path blue means that I have a Q mark there. If I have a Q mark crossing here, I kind of split this box and this box. They get two crossings, which two independent things. So here is the price I pay for this. No, because we had there the estimate on the renewal. So just to do the end, just every side. So just the volume of the space box. And now I need to control the probability of having this crossing inside of this box. Now recall that here, this is Bn minus 1, and on the space, it's bigger. No, it's 2 to the n. It's a scale n. So you need to find a way to get up to something that relates to the scale n minus 1. But you just see that this guy, to the n, you split into 4 pieces, which correspond to the half box of scale n minus 1. So you have these guys here. And now you are saying, well, if I have a path that time crossing, there are 2 options. This time I look at this path and I just look from above and see what it covers in space. If it stays restricted, to guys, how many of these fix one direction, it's easier, no? Because we need to If it stays restricted to 2, then I will have a time half crossing. So that's this part here. If it's not restricted to 2, then I'll have some special crossing. I just need to count how many of these possibilities do I have. So for each of them, we are going to end up controlling this probability, which I had before, of crossing one such box by something that involves the previous scale. So now if you go and put together, you are going to end up with an estimate. Of course, I need to do something similar for the space half crossing, but it's easier, but it's very similar. It's easier because in space, things are independent, so you don't have to pay this extra price. And putting the two things together, you get a recursion that goes in this way. So this is, and so here probability, you get this. Now you need to make some computation, which is not probability, it's just analysis. And to say something on f, on the function f, such that if you have this at scale n, you are going to have the same thing at scale n plus 1 for this recursion. And you compute, and you see that if you take f like that, with theta related to Bn in this way, then it works. So now you just need to show that if your lambda is small enough, you do have some the beginning to start with, the trigger, let us say. Now that's some scale for which it will happen, and then everything will go through from the recursion that you have. So our condition comes from this. It's sort of really, in this sense, it's technical. No, just there is, we couldn't go beyond that to get something. I mean, it's natural to guess. We do have examples where the tail, which is in the domain of attraction of a stable 1, and still lambda critical is 0, but it doesn't have the example we have. I mean, it has no finite first moment. So that's for the moment. That's what we know. There are some analogous results for the edge case, and these results on the edge case, they were motivated because by the problem that Danielle is going to talk about. That's what led us to say, let us look at what happens on the edge when the general renewal process stay on the edge. But I don't want, also I don't have time. I don't want to enter into that. And so I'm open for questions. Thank you very much. And these are the references.
Thank you very much for a good talk. Are there questions?
Someone had asked the question in the beginning, and maybe I didn't understand. I don't know if now this question vanished or if I should try to understand it now and answer.
It is probably my
Oh,
turn.
it was you, Anna. Thank you. So if you...
Thank you. Yes, I was basically asking, you were talking about determining the levels, Li. L from 0, I think, to...
You mean the else?
Number? Yes, here.
Yeah, the else.
Yes. So if you...
It's...
Sorry, sorry. Basically, the question, if I may, is basically about the I, so the number of these levels. Is given a graph that you analyze, is this number based on the condition that you have fixed, or can it be random? I mean, what are the limits? What are the properties of this number of levels that you have in a graph given this instruction?
I think that since I want to prove survival, it suffices for me to use a line, Because if it survives I have an infinite path in my graph, and the process will be able to stay forever only on this path without even infecting the others. So that's why I look at the a half-line, in fact, because here it is, I have an interval of time t of a given distance. I'm looking at 4 times, say this is t, this is 4 times t. So what's the probability that I have no renewals between in an interval of less t up to 40? This 4 is fixed. I'm going to use this 4 always. So this probability is always the probability that I don't have is bounded from below. So how long does it take me to find someone like that? It's always bounded by a geometric. The probability that I don't find after I steps decays exponentially in I. I don't know if I am, but it's enough to look at the line for survival, even if your graph is very complicated. For the other question, it's, I don't know, for extinction, that is a proof that uses ZD. Because, I mean, more general graphs, one has to depend on the degree, you know, but one can probably do something, but bounded degree.
Just one additional small question related to this. Is it always possible to exactly compute the levels on this formula?
What is exactly, you mean this one?
I mean, the exact LIs, the exact levels. Or could there
you
be
mean
problems in the algorithm or in the determination?
I take the first. It's a random.
Okay.
It's a random L for me.
Mm-hmm.
The only thing that I know, it doesn't take too much to go. So I will be able to, now it will be important how this distance is related to the time, because I need a Poisson process to travel there with very large probability. But that's kind of simple, huh?
Okay.
All that matters is the distance between them in comparison with the length of the time. So I want a Poisson process to get farther than a certain distance within a given time. So this distance has to be smaller than t to have it large, good probability.
Okay, thank you. This, I think, answers also to the first question. Thanks.
Are there more questions? If it's not the case, I suggest that we make a pause of 5 minutes and we come back to the talk of Daniel. Thank you very much, Maria Eulàlia.
Thank you.
É.
Daniel, você viu que eu mandei e-mail para você hoje, né?
D'ailleurs, tu sais qu'à partir du 1er janvier, les gens ils vont pouvoir passer le permis et conduire à partir de 17 ans. Si c'était passé avant, ta soeur elle aurait pu aller toute seule au lycée.
Maybe, Daniel, you want to share your slides already? Perfect.
Yeah. This good?
Yep.
Maybe I'll leave it like this so that I can see the. Yeah.
Well, welcome back to the One Word Probability Seminar. We are ready for our second talk of the day, which will be in charge of Daniel Valesin, who is a professor in the University of Warwick, and he's a world-class expert on the contact process. And we are looking forward for your talk, Daniel. Thank you for being here.
Okay. Thank you very much, Adrian and Alberto, for the invitation. It's a great honor. I like this seminar very much. I think, like probably many people in the audience, I was there in the first One World Probability Seminar that was during the pandemic, and there were hundreds of people there. And it's a very dear memory to me because it was a time when, you know, people were looking for a community and reaching out, and then we could like see this beacon of light, and the community was still there. So that's a very good memory in a bad time. So I will talk about a part of this paper with Eulàlia and also Marcelo Hilario and Daniel Ungaretti, and it will be about the contact process on a dynamic environment given by dynamic percolation on ZD. But I thought, since I'm going to talk about this, it was a good idea to spend some minutes giving you some history of the contact process on random environments, both static and dynamic random environments. So I'll perhaps spend some 5 minutes just to convey the idea that there's a large literature on the contact process on random environments. So so the intensive research on contact process on random environments or random graphs also, but mostly static. And of course, the focus is how the various aspects of networks affect the infection spreading, because, well, if we want the contact process to be a model for infection spreading, then we should not only study it in ZD, because you can argue ZD is not a very good model for any real world biological network. You should also consider other networks. And so there are many works, large literature. So here I'm just selecting a few highlights, some papers that are kind of important to me. So I guess you can start counting, consider a first paper on contact process on random graphs. This one by Pimentel. I guess you cannot see my cursor, so I'm going to use this purple color and let me make it thicker. Okay. Yeah, so this was a paper by Pimentel where he considered contact process on trees and proved that there is this phenomenon of double phase transition for the contact process on trees. And he also considered Galton-Watson trees in that paper. The next highlight to me is this paper by Chatterjee and Duret, where they studied the contact process on finite power law random graphs. And the main point there is to show that the infection stays alive on these graphs, even if lambda is very small. And the phenomenon is that, you know, there are some vertices with very high degree and they sustain the infection for very long. And essentially it's a game of these vertices maintaining the infection and sending the infection to each other. So the infection stays alive for a long time, even if the infection rate is very small. Recently, there's been this, what I consider breakthrough paper by Midinam, Nguyen, and Sly, where they consider the contact process on various random graphs, but in particular, the supercritical sparse Erdős-Rényi graph and prove phase transition there. But of course, I'm omitting here large body of literature, so there are many papers about contact process on random graphs. For dynamic environments, not as many. I listed a number here, and I'm immediately anxious that I forgot important ones. But I will start my historical review with these two papers by Eric Broman, 2007, where he considers arbitrary graphs, and it's a contact process in a situation where, you know, the rates of the contact process are governed by an underlying Markov chain. And the focus of these papers is on stochastic domination, so comparison between various processes and conditions under which you can say one process dominates another. Then we come to a paper by Daniel Remenick, 2008, which is already ZD, and it's an environment given by sites which can be blocked to the infection or susceptible to the infection. This paper is already very much in the spirit of the one that I'll focus on today. Then there is these two papers by Emanuel Jacob, Peter Morters, this one also with Amitai Linker, which is finite power law random graphs and with an edge update dynamic. So there is a clock that rings in a vertex, for example, and the vertex decides to rethink their friends from time to time. And then they study the impact that this has on the infection. There is then Linker and Remenick 2020, which will be the main. I'll spend some time describing what they do in this paper because we build on what they do here. And this is vertex transitive graphs, but mostly ZD, and the environment is given by dynamic bond percolation. And this model and results have been generalized recently by Anja Sturm and Michael Seilert to more general dynamic random environments. There's also this paper by myself, Gabriel Batista da Silva, and Roberto Imbuzeiro Oliveira, which is about random irregular graphs with an edge switching dynamics. So these are the few papers that I could remember on contact process on dynamic random environments. And some questions that people typically want to answer are, so what's the major difference? So what happens when you introduce an environment dynamics, both in terms of phenomena and in terms of the techniques? So do the techniques that apply to static graphs also apply to dynamic graphs? So yeah, that's captured by these questions here. So in particular, does the environment dynamics help or hinder the infection? So sometimes here we come to some monotonicity type of question. So let's say there is a parameter governing the speed of the environment dynamics, if you change this parameter, is that better for the infection or not? So these kind of questions are usually extremely interesting, but tend to be hard to answer. So that's it for history. And now my next section is about this paper that I mentioned by Amitai Linker and Daniel Remenik 3 years ago. And so I have to resist the fight against the risk of spending all my time talking about their paper, because it's an extremely nice paper and they prove many nice things. So the model is we take a vertex transitive infinite graph, and I think for the intuition and also for the results, it's I think we can keep thinking about ZD. So most of what they do works on vertex transitive graphs or ZD, but there's only one theorem that they prove that is only Z, only dimension 1, and that's the theorem that we extended to higher dimensions. So that's the theorem that I'm going to talk about eventually. So briefly, let me describe the model. So we have an environment process, which is as follows. It's just you take two parameters P and V, and we're going to, so it's going to be a process on the edges. So every edge will be open if this zeta t of the edge is 0, closed if it's 0, and open if it's 1. And the edges they update independently, and so the rate at which you have a transition from 0 to 1 is a V times P, and the rate of 1 to 0 is V times 1 minus P. And when you do that, you make it so that a Bernoulli product measure is stationary for this environment process. Right? So every edge is open and closed independently of all the others with probability P or 1 minus P. So that this stationary measure only depends on P, but V is describing the speed at which this dynamics takes place. And this model has been studied quite a lot on its own, and it's usually called the dynamic percolation in the literature. But here we take this as an environment for the infection, right? And the idea is that the closed edges will be those in which the infection cannot travel, and the open ones in which it can travel, so transmissions can occur. So we have a contact process, which I would denote like xi, and that's on 0, 1 to the vertices, and the parameter of that is lambda as usually. So xi 1 means infected, 0 means healthy, and the transitions at a vertex u, or I guess I should write here x instead, at a vertex x it goes from being infected to being healthy with rate 1. And it goes from being healthy to infected with a rate that is lambda times, well, it's the number of infected neighbors, but with the restriction that the edge between the two has to be open. So it's like a vertex decides to transmit to any neighbor with rate lambda, but the transmission can only take place if the edge is available at that point in time. So these are the dynamics. So there are three parameters, P, V, and lambda. And I also have to specify how it starts. So I'll always take the environment in equilibrium. So this is, product Bernoulli P. That's how you start, and that's where you stay, in the distribution of the environment. And for the contact process, we start with a single vertex infected. And that's because the kind of question that we'll address, at least in this talk, is questions of survival and extinction. Is it possible that the infection lives forever or not? And for this type of question, it doesn't matter if you start from one vertex or if you start with any finite number of vertices. The probability will either be 0 regardless of where you start, or it will be positive regardless of where you start. I mean, of course, the specific value of the probability depends on depends on the number of vertices, but the feature of being 0 or non-zero does not depend. This process admits a Poisson graphical construction, just as Eulàlia described. The only difference here is that now there are also Poisson instructions on the edges that tell you now this edge should open, now this edge should close. But apart from that, everything is the same. And you also have this notion of infection path, right? So if you have, let's say, a vertex X here and a vertex Y, and this is like the time, or let me put another one here. So an infection path is something that perhaps starts at X and then it moves here, transmits to Y, then it moves here, transmits to Z. And it should never, we should never touch these recovery marks, which appear with rate 1. But also every time that there is an arrow like this, we have to make sure that that this edge is available at that point in time. And so I suppose the audience can understand how this is done. It's a pretty standard graphical construction. Spend more time introducing notation or anything. So you can define a critical value for the infection rate, and it's denoted in the paper by Linker and Remenick by lambda 0 of V and P. So yeah, perhaps one thing I should have said already is that this process is monotone in lambda. So if you increase the infection rate, of course, you will have a process that have more infections, right? So monotonicity in lambda is clear. So we can define this critical infection rate lambda 0 as a function of V and P, which is the supremum of the values of lambda, so that the process dies out. And dying out here is the condition that probability that, well, there exists T, so that the process started from only the origin infected becomes identically 0. Is equal to 1. So that's what dying out means in this talk. So as I already said, there is a monotonicity in lambda, and it's also easy to see that there is monotonicity in P. So if you increase P, that means that you put more edges being open. So that means that, becomes easier for the infection to survive. So that means that the supercritical phase increases. So that means that the critical parameter decreases or does not increase. So this function from P to lambda 0 VP is not non-increasing. So dependence on P is straightforward. Dependence on V is not at all clear. So when you increase V, on the one hand, you're adding more vertices more rapidly, but you're also adding more edges more rapidly, but you're also removing edges more rapidly, and it's not so clear how what the net effect is. So there is no statement being made about monotonicity in V, apart from this proposition here proved in Linker and Remenick, which is that this function that takes V into 1 over V lambda 0 VP is non-increasing. And this is just a very short, very soft argument with a time rescaling that I can very quickly sketch here for you, if I can clear some space. So the argument is goes as follows very quickly. So if we take the contact process with, let's say, rates lambda or P, the process with lambda P and V, then the transmissions happen with rate lambda. The cures always happen with rate 1, and the edge updates, they happen with rate V. Then you take this and you do a time change. So let's say you take, suppose that you fix V prime larger than V, and suppose that you speed up time by a factor of V prime over V, which is more than 1. Then you get a process in which, by the way, think of this as a little table that I'm drawing here. So you get a process where the new transmission rate is now V prime over V times lambda. The new cure rate is V prime over V, and the new edge update rate is V prime. Yeah, so you get a new process in which you have these rates in which things are happening. And now this process is stochastically dominated by a process in which, you know, the transmissions are again the same, the cures are 1, and the edge updates are V prime, but this one is just the contact process with rates V prime over V lambda, and then P, and then V prime. So by doing this time change, I moved, and using a stochastic domination, I moved from this one to this one. And now if you work out a little bit what this means in terms of the critical lambda, you will see that it's exactly this the fact that this function is non-increasing. So it's just a very soft argument using this time change and then stochastic domination. Okay, so another thing that they prove in their paper is that the limit when V goes to infinity of lambda 0 Vp is lambda bar over P, where this lambda bar is the critical rate for the contact process on G here. I mean the graph, so let me write ZD. This is when you are speeding up the environment. Well, the speed of the environment is going to infinity, and the idea here is that when the environment update is going to infinity, your things are happening so fast that you have you know, from one time that you use an edge to the next time that you use an edge, you forget all the information. So it's like you're resampling the edge. So morally, what that entails is that it's like a thinning of the transmission process, because every time that you try to transmit through an edge with rate lambda, you have to toss a coin with probability P to see if that edge is open. And then this limiting situation, this limit here is exactly what corresponds to this thinning. But they actually prove it using stochastic domination techniques from these papers by Eric Roman that I mentioned in the beginning. Okay, so as I mentioned, the interest is in studying these models is to identify new phenomena. And one new phenomenon is this thing called immunity. Immunity means that you have certain pairs of the parameters V and P for which lambda 0 is infinity. Lambda 0 being infinity means that every lambda is subcritical. That means that no matter how high the infection rate, the process cannot survive. So these are choices of V and P. So think, for example, P very small, so most of the edges are closed all the time. Let's say V also very small, so the environment is frozen. Then, you know, even if lambda is very high, you would expect the infection will not make it. So that's what is called immunity, is when this immunity region is the pairs VP for which this phenomenon occurs. Lambda 0 is infinity. And here's a theorem from their paper summarized in a picture. So this is the diagram with the parameter V in the horizontal axis and P in the vertical one. And they prove that there is a certain value P1 that is strictly between 0 and 1, so that this immunity region is as I drew here. So what is formally known is what is written here, but if you know, you should not worry too much about what is written and focus on the picture. So what they prove is that, you know, if you fix any V and you move downward, so you take P small enough, you will eventually land in the immunity region. So this purple zone here that is shrinking, it never becomes empty as you move to the right. Yeah. Moreover, with their arguments, you can see that this curve here is non-increasing. It's not known to be strictly decreasing, but non-increasing. And yeah, that if you take P above P1, then there is just no immunity. So, along this line here, this horizontal line, there is no immunity. So for any choice of V, you know, the process survives for lambda large enough. So this is what they prove on ZD, or in fact on any vertex transitive graph. I hope the contents of their theorem is clear. As I said, there is one little thing extra that they only prove in for Z. Trying to erase the things that I drew now. Okay. So in Z, they prove this condition here, which I will spend some time on because this is the main thing for me today. It's the following. For any value of P that you take, doesn't matter if above P1, below P1, any value of P, and any choice of lambda, yeah, the contact process with parameters lambda, V, and P dies out if V is small enough. So morally, this means that, you know, if you fix the infection rate, no matter how high, if you fix P, no matter what, you can kill the infection by freezing the environment. So if you slow the environment enough, the infection will die. You can kind of, and then this is equivalent to saying this thing that is written here, but, you know, at least when I see this kind of talk, I find it confusing to think about the critical value. Does it increase? Does it decrease? So I'll try to focus on what is written here instead. So you should understand this by saying, okay, I fix a certain P. This is in dimension 1. So what happens is that you have, you know, edges missing here and there. Edges. So Z is broken into these intervals, and the infection is happening inside these places. So infection spreading. But then, you know, if you take V very small, what is happening is that you're freezing these islands. Yeah, these blue islands are being updated very slowly. And then the infection dies out in each of them before anything else happens. And then it dies out everywhere. So that's what this is saying. So once more, given lambda and P, you can kill the infection by freezing the environment in dimension 1. And then they don't say anything about this in dimension higher than 1. And in fact, if you think about this intuition that I just gave, you should imagine that this should not be true as written in dimension higher than 1. The reason it should not be true in dimension higher than 1 is that in dimension higher than 1, well, percolation is non-trivial, right? There is a supercritical phase of percolation. In dimension 1, there is no supercritical phase of percolation. In dimension higher than 1, there is a choices of P where you have a supercritical percolation cluster. And then, you know, if you freeze the environment, the infection will not care because it can happily travel in the supercritical cluster. So there should be, this statement should be reformulated in dimension higher than 1. So now, okay, I'm done talking about their paper, and I'll talk about what we do in our paper. So in the rest of the talk, we take ZD with a dimension 2 or higher, and we let PC be the critical parameter for Bernoulli bond percolation on ZD, and I hope that's what that means is clear to everyone in the audience. So here's our theorem. So this is Eulàlia, Ungaretti, Vares, and myself. So it says that on the one hand, so this is the part that is similar to the one done by Linker and Remenick in dimension 1. It says that if you're in the subcritical percolation phase, you can still kill the infection by freezing the environment. So if P is subcritical, lambda is 10 to the power of 10 to the power of 10, you can still kill the infection by freezing the environment. Yeah. And part B says that this is not so if P is above PC. So if P is above PC, then if you take lambda to be 10 to the 10 to the 10, then you can do whatever you want with V, the infection will survive. Right. So these are the two parts, and I should mention they are not of comparable difficulty to prove. So part A is much, much harder than part B, because part A, you might say, okay, but part A was already done in dimension 1, so can you just repeat the proof? And the answer is no, we could absolutely not repeat the proof. So part A, the proof was done by multiscale renormalization techniques. And part B, I wouldn't say that it's an easy proof, but it's much softer than it. Okay. So yeah, in particular, yeah, if you remember, there was this P1 that appeared when I showed their theorem, which is when the immunity regime immunity region begins, well, below which the immunity region begins. And what our theorem says is that, this P1 is smaller than or equal to PC. We don't know if it's equal to PC. I mean, we believe it's smaller than PC just because in dimension 1, it's smaller than PC, right? In dimension 1, PC is equal to 1 and P1 is smaller than 1. That's all I'm saying here. And so we believe that there is this intermediate region where, between P1 and PC. So, let me say a few words on the difficulty of proving of the case A. So this is here difficulty of treating P smaller than PC, or of proving part A of the theorem, is that even when you take lambda to be large enough, the infection rate is large. If you have the small percolation clusters, these are finite graphs. So on finite graphs, the contact process will eventually die, but it will take very long to die. And here I just mentioned this theorem from 2016 by Tom Mumford, Jean-Christophe Mourac, Yang Yao, and myself, which says, so don't pay too much attention to this theorem because it's kind of a side remark. But what it says is that if you take lambda above the critical threshold for the contact process on Z, and you take an arbitrary graph, so G here is a finite connected graph, and we have to say that the degrees are bounded, then the time it takes for the infection to die, so it takes very long for the infection to die. So it takes a time that is exponential in the number of the vertices, and this is for any graph. Just bounded, there's this bounded degree assumption, but so sufficiently infectious contact process will survive will be metastable, will survive very long on arbitrary graphs. So in particular on these small percolation clusters. So they are small there. If you take P much smaller than PC, you have tiny clusters here and there, but still you could argue that the infection is surviving for an insane amount of time in these clusters. And in the meantime, maybe, they're being joined together. I mean, intuitively, it should not happen, but you have to rule it out, that the infection manages to survive by traveling from cluster to cluster. And that kind of suggests that a multi-scale argument is going to be necessary because, you could have parts of the world where an anomalous big cluster appears, and then, you have to come up with some procedure to say that they don't matter too much. So I have a very sketchy sketch of the proof of this. It's a multi-scale renormalization argument. I definitely don't want to give a very technical rest of the talk. So it will be considered this a cartoon of a proof, okay? So we take P smaller than PC of percolation and lambda ridiculously large. Think of lambda as being incredibly large. And we want to say, we want to prove that if you freeze the environment, if V is small enough, if the environment is sufficiently frozen, the infection will die. So what we do now is we'll fix V very small, and during the proof we'll see how small it has to be to kill the infection. Okay. So it will be multi-scale renormalization, and there will be boxes, and part of this was already in what Eulàlia explained. So we'll take a space-time box of this form. So L is the spatial, the side length of the box, and H is the height in time. And you can imagine that there is a graphical construction inside the box for both the environment and the contact process. So you have these Poisson instructions going on. And then you have a bunch of these half-crossing events, which is the event that, there is an infection path crossing half of the box. And half of the box means in either of the possible ways to divide it in half. So either vertically from bottom to top, or vertically from the middle to the, vertically from the bottom to the middle, or from the middle to the top, or, like what is drawn here, or like this, or if you divide it in the other way, like this or like this. So there are this all these half-crossing possibilities, and you want to consider these half-crossing events, and basically you want to say that that the probability of these half-crossing events is very small when the box is large, because we're trying to say that the infection dies. Yeah. And there will be scales. So these boxes will come in different sizes, in scales that grow geometrically in this case. So the scales will be we'll have to choose scales to start with. So there will be L0 and H0. And then they will grow geometrically. So there will be a parameter alpha for the spatial growth, and there will be a parameter beta for the temporal growth. So here's a little picture of the level K box, right? So LK and HK. And as I said, we need to prove that the probability of half crossing at level K goes to 0. So this is all for V small enough, which we haven't chosen yet. For V small, when you take K larger and larger, the probability of these half crossings goes to 0. If you prove this, more or less, you're saying that the infection dies out, because, you know, if the infection were to survive, I think there's something in the chat. Did anyone ask a question? Ah, yes. Could there be other ways to freeze the process on a graph? Yes, I mean, you can define other various ways of various other environment dynamics, which I suppose what matters a lot in this kind of result is you know, how quickly mixing the environment dynamics is, because you want to have independence in different regions of space-time. So if you take another freezing dynamics, another environment dynamics, you have to worry about about dependencies appearing, and then the techniques can become much more complicated. Well, the advantage of dynamic percolation is that everything is very fast mixing, right? And everything is independent in different edges. So that's in a way the easiest environment easiest dynamic environment to work with. But yeah, what I was saying is that we now want to say that the probability of half crossing goes to 0 when you take the boxes larger and larger, because then that says that the infection cannot survive. Because the contrapositive of this is saying that if the infection survives, then you know you have crossings on all scales. Okay, so the way we do that, and is the typical renormalization kind of scheme, you argue that if there is a half crossing of a level K box, then there is a half crossing of two level K-1 boxes that are far from each other. So if you have this level K box and there is like a half crossing here, then you can find, say, a smaller box here and a smaller box here. So they are, you know, kind of far from each other, and they are both half crossed. And the whole reason for taking half crossings rather than crossings is to take care a little bit of the geometry, because, you know, it's an oriented kind of percolation setting. So it's to make it so that the geometry works, but don't worry too much about that. So we do this implication here. We say, okay, if level K is crossed, then there are two level K-1 crossings. We iterate, so we apply the same reasoning in this box and this box. So now we get two tiny sub boxes, one here and one here, and then one here and one here. We iterate again and again, and we end up with, if we do this until, you know, the level of sand, so the bottom level of this, you get a certain set of 2 to the K level 0 boxes. And these level 0 boxes, they are pretty spread out in space-time. Here I wrote space, but I mean space-time, right? Because it's oriented. So typically they will be spread out in this kind of fractal structure. So there will be, let's say, 2 of them here, 2 of them here. So this pair, they're far from each other. Then there's already a group of 2. This distance is big, so I can group them like this. Then I group these groups like this, so it has this kind of contour set flavor to it. And the reason we need to do something like that is that, you know, if they're distant from each other, you get kind of independence of what's happening inside these different boxes. Let me call calligraphic X this collection of level 0 boxes, these 2 to the K level 0 boxes. And then the argument goes by saying that, you know, the probability of having the level half crossing at level k is, so this here is a huge, a colossal upper bound. So you upper bound on all the possible way to choose this contour, this fractal set of 2 to the k boxes. And you consider the probability that all of them are half crossed. So all these level 0, here I forgot to say all level 0 boxes in X are half crossed. So this is like this big upper bound involving 2 to the k events. And I upper bound it further by the number of ways to choose the fractal set by the worst case scenario. So the probability, if you choose the worst calligraphic X, what is the probability that all of them are half crossed? Now you do some easy combinatorial computation, and you say that this number of choices of X is something along these lines. So it's it grows exponentially. It's like e to the power of 2 to the k, and there is a combinatorial factor here which depends on alpha and beta, where alpha and beta are the scales of the growth coefficients in the renormalization. So the game now is to study this supremum here and to say that it more than compensates. So this number here is of course very big, and we want to say that this number is very small. And what we have to choose, well, we have V to play with. We can take V very small so that this number becomes very small. Yeah. In fact, there are many things to choose in this construction, and here they are. There is alpha and beta, which are the growth coefficients. There is L0 and H0, which is the size of the bottom side, the dimensions in the bottom scale, and there is V itself, which is the thing we make small. So I will just now, the last thing I'll mention about this is the order in which things are chosen. And I hope with this order, I convey a little bit the idea of the argument. So the order is as follows. Alpha turns out to not matter at all. So the growth of the scale, the space coefficient, we just take it to be 4 or 6 or whatever, something like that. The next thing we choose is L0. So L0 is the spatial size of, you know, the bottom scale box. And the way we choose L0 very large so that, you know, you start to feel that you're in a subcritical percolation. So this L0 should be very big so that all the little clusters, all the percolation clusters here should be like smaller than a constant log L0 with high probability. You know, because if P that you fixed in the beginning, if that P is not too far from PC, you know, it could be that you have to take a very large box to start to feel the subcriticality. So you take L0 large so that you can indeed feel that the percolation is subcritical and that these clusters are all tiny. After you start feeling that the clusters are all tiny, you choose H0 in the following way. So now these clusters are tiny, but as I mentioned at some point earlier, the infection survives for a very long time in each of them. So survival of the infection, survival of the infection. So now you take the height of the box to be so immense that even if they survive, if the infection survives for a long time in these little clusters, it would die out in all of them in this time interval 0H0 with high probability. And by the way, and when I say this, sorry, I should have said. Here, I'm pretending that the environment is frozen, right? So in this choice of H0, I say, if there were no edge updates, so if the environment were completely frozen, then the contact process on these tiny clusters would all die. So now we chose L0, H0. The next thing we choose is V, so that now, you know, now that the bottom scale box is chosen, you can take V so small that indeed it's as if the environment were completely frozen in these bottom scale boxes. Yeah, so V is so small that the density of edges that update on this time horizon is tiny, and so that indeed the dynamics in these bottom scale boxes is effectively as if it were completely frozen. And finally, the last thing that is chosen is beta, which is the coefficient in the renormalization in the time separation of the boxes. And the idea of choosing beta large now is that, if in the renormalization, so let's go back to this Cantor set. If in this Cantor set, you have a box that is on top of another, if you observe the environment in the bottom box, that will give you information on the environment on the top box. So this vertical alignment or horizontal vertical alignment, one box being on top of the other, this is bad in terms of dependence, right? Because so you choose this beta very large so that this distance, this minimal distance between two boxes, one on top of the other, is still very large. So there's mixing in the environment, and you recover independence. So where was I? I was here. So you choose beta as the last thing. And then when you have made all these choices, then the renormalization can fly. And you can say that the process dies if V is small enough. I also had a scheme here to show the proof of P larger than PC. But as I said, that's much easier. I still find it interesting, but maybe for the sake of time, I'll stop here. So thank you very much.
Thank you very much, Daniel, for a very nice talk. Are there questions? Well, an obvious question is, can you tell us a bit of the case P bigger than PC?
Okay, okay, let me do that. I hope I can do it in 2 minutes or so. So here's how it goes. Take P larger than PC. So now you have supercritical percolation. And what you want to prove is to say that, well, the process now, if you take lambda very big, yeah, that the process survives no matter what is the choice of V. Yeah. So P is fixed, lambda is now fixed, and you want to say that no matter what V is, the process survives. Then, with some reasoning that I will not really detail, it's sufficient to consider, V in an interval like this, to say that for V between 0 and a certain V bar, the lambda 0 is finite, meaning that there is a survival regime. So you want to say that, yeah, you fix this V bar, and V is in this region, and you want to say that when lambda is very big, you survive wherever V is. So it's also a renormalization, the argument, but it's not a multi-scale renormalization. It's a one-step renormalization. And so again, we take a space-time box. The spatial time is 0L to the D, but time can be just 0, 1. And I'll just describe to you what happens inside this box. And the argument that I'm about to give you should be kind of uniform in V. Yeah, at least for V inside this interval 0 V bar. I will describe to you a way the infection spreads a lot inside this box, but in a way that is uniform in V. So you take this box and you suppose that this L, which is the size of the box, is very large. And then, P is above PC. So in the floor of the box, there is this giant component. Yeah, there's this supercritical component, and it's more or less locally dense. So it's occupying with the density, any sub box that you fix here, you will see this giant component present there. And now, the scales of this box are fixed. What you do is you take lambda absolutely huge, so that, if there is one guy infected in the giant component in the box, immediately the giant becomes all infected. So this guy spreads to the neighbor, so everything becomes infected. And now, because we're taking V, between 0 and a certain value V bar, what you do, you can argue that there will be a moment when there will be an edge update. But you can say, okay, an edge updates, but after this edge updates, immediately, maybe you broke a little bit of the connected component. Now that the giant changed a little bit, but immediately the infection voraciously, conquered everything else in the new giant component. So between edge updates, the infection just eats up everything that it can eat. And this happens until time 1. So this box will become full from the infection. And then what we do is we say, okay, there's this box. Now there is an adjacent box that is a little bit higher up in time. Then there is another box. And then this infection keeps traveling from box to box. Of course, you can't do it just box and then the next box because, well, by Borel-Cantelli, it would eventually fail. But you can do like an oriented percolation kind of block argument to say that it survives forever. So that's a rough sketch of how it goes.
Thank you very much. And I see that there is a question by Andre.
Thank you. Great presentation.
Thank you.
And the question relates to, is there anything known about scaling limits of this process in higher dimension?
So one thing that I know is, so in this paper that I mentioned by Anja Sturm and Markus Seiler, they prove a shape theorem for this process. So that means, you take, you start with one vertex, and let's say you take it in the regime where the infection survives, because otherwise it doesn't make sense to talk about scaling limits, right? But let's say take infection surviving, and you take, you run it until time t, and you consider the set of sites that have already been touched by the infection by time t. So this is like this random set. And then a shape, what is called a shape theorem for the contact process, is to say that, if you take this set, you divide it by t, so that it becomes a order 1 size. This will converge in some sense to a compact convex set. That's a shape theorem for the contact process, and they do prove it for this one. And apart from this, I'm not aware of any other scaling limit kind of result.
Okay, thank you.
Thanks for the question.
May I also ask a question? This for P less than PC, you gave this multi-scale argument.
Yeah.
My memory is not so very good, but I have a feeling I've seen similar multi-scale arguments in dependence percolation. So can you say a little bit about where that argument comes from? What's the origin of that sort of arguments?
Yeah, for sure. Oh, the origin is a bit tricky. I can perhaps tell you where I learned it from and where we took it from in this paper. I guess, and I don't want to say anything unfair here, but the way I started getting into these things was from random interlacements, so models of percolation with dependence, and yeah, so I guess my co-authors have dealt with percolation in other contexts and have similar renormalization schemes. So it's a thing that popped up in several places. I guess the place where I learned it from is the literature of random interlacements from papers from Sneedman and Balashrath.
Yeah, this was also sort of my memory, but it's worse than yours. So thanks.
Thanks for the question. I think Sam has a question.
Yeah, so I was wondering, you've done this for ZD, and then perhaps the next most popular percolation is on the complete graph to get Erdős-Rényi with some sort of sparse supercritical case.
Yeah.
Do you think similar methods could apply? Of course, it's finite graph, so you want to say some things like not survival forever, but sort of long-term survival. But do you think similar things could be done?
That's a tricky question. I would say the same. There's very little. Well, for the P above PC, I would say many of the ideas probably will, this thing that you have a giant component, lambda very big takes over the giant component. This kind of idea, I think, could be applicable in the Erdős-Rényi kind of complete graph kind of setting. For P below, what is even PC? Yeah, so for P below PC in that case, we're talking about sparse Erdős-Rényi in the subcritical regime, right? But things are so
yeah, just like constant over n with constant less than 1.
Yes, so there I would be I would say the kind of argument that I show has very little hope of working, right? Because then I think it's more about looking at contact process on Galton-Watson trees, saying how long it. I think it's a very interesting kind of question, but with very different techniques. And yeah. So that's
Cool. Thanks.
thanks for the question.
Is there another question? If it's not the case, we thank you very much, Daniel.
Thank you.
Again.
Thank you very much, everyone. Thanks.
This was the last one word for Alberto and myself. So thank you for this nice period.
Thank you, everyone. And I think hopefully the one word probability seminar will resume in September or in autumn with the new organizers.
Thank you.
Okay, thank you very much. Thanks.
Thank
Thank
It's
you
a
very
pleasure.
much, huh?
Yeah.
Thank you,
Yeah.
Alberto.
Thank you for the
Thank you,
organizing
Adam.
as well.
Yeah, thank you for all this organization.
Yeah, thank you.
Bye.
Okay, bye-bye.
Bye.
Take care. See you soon. Bye.
Take care. Have a good summer.
Yeah.
Oi.
All of you.
Tchau.